How an AI-driven wearable device translates thoughts into text. Researchers at the University of Technology Sydney, UTS, have engineered a groundbreaking portable device that converts brain activity into written text with an accuracy of approximately 40%, eliminating the need for invasive implants or surgical procedures. Developed by the UTS Artificial Intelligence Center, this innovative system represents a significant advancement in bridging the gap between human thought and technology. By decoding silent thoughts and transforming them into readable text, the device offers transformative potential for individuals with communication challenges, such as those with severe speech impairments due to conditions like amyotrophic lateral sclerosis, ALS, stroke, or locked-in syndrome. This non-invasive technology opens new avenues for assistive communication, enabling people who cannot speak to express their thoughts in writing. While the system currently achieves a 40% accuracy rate, the research team, led by Chin-Teng Lin, director of the Graphenex UTS Human-Centric Artificial Intelligence Center, is working to enhance its performance to reach a 90% accuracy level, comparable to modern speech recognition or language translation software. Such an improvement could revolutionize accessibility, making the technology a practical tool for everyday communication. This study is a pioneering effort in directly translating raw electroencephalogram, EEG, signals into language, marking a significant milestone in neurotechnology and artificial intelligence, Lin stated. Our goal is to create a seamless interface between the human brain and external devices, empowering individuals with communication barriers to interact more effectively with the world. How the technology works. The UTS system employs a wearable cap equipped with electrodes that capture electrical brain activity through the scalp via EEG. In the study, 29 participants silently read passages of text while wearing the cap, which recorded the electrical signals produced by their brain's neurons. These signals are then processed by an AI model named DeWave, developed by the UTS team. DeWave segments the EEG waves into distinct units, each representing specific patterns or characteristics of brain activity. Through extensive training on large datasets of EEG signals, the model learns to map these patterns to corresponding words and sentences, effectively translating thoughts into text. Unlike previous brain-to-text systems, which often required invasive procedures like brain implants or relied on bulky equipment like functional MRI scanners, the UTS device is entirely non-invasive and portable. This makes it more practical for real-world applications, as it can be used in various settings without the need for specialized medical facilities. The system can also function with or without eye tracking technology, further enhancing its versatility compared to earlier methods that depended on additional aids to interpret brain signals accurately. A leap forward in neural decoding. The research introduces a novel approach by incorporating discrete encoding techniques into the brain-to-text translation process. This method breaks down EEG signals into smaller, manageable units, allowing the AI to identify and interpret specific patterns more effectively. The integration of discrete encoding with large-scale language models is pushing the boundaries of both neuroscience and artificial intelligence, Lin explained. This approach not only improves the accuracy of neural decoding, but also opens new possibilities for understanding how the brain processes language. The study's use of a larger participant pool, 29 individuals, sets it apart from earlier research, which often tested brain decoding technologies on just one or two subjects. EEG signals vary significantly between individuals due to differences in brain anatomy and neural patterns, making it challenging to develop a universally applicable system. By including a diverse group of participants, the UTS team has created a more robust and adaptable technology, capable of accommodating a wider range of brain signal variations. Performance and challenges. The current system achieves a translation accuracy of around 40% on the BLR-1 metric, a standard measure that evaluates the similarity between machine-generated text and high-quality human translations, with scores ranging from 0 to 1. While this represents a significant achievement, the technology faces certain limitations. According to Yiken Duan, a lead researcher on the project, the model is more adept at identifying verbs than nouns. For nouns, it often generates synonymous terms rather than exact matches, for example, translating the author as the man. Duan attributes this to the brain's tendency to produce Hula-Eeg patterns for semantically related words, which can complicate precise translations. Despite these challenges, our model produces meaningful results, aligning keywords and forming coherent sentence structures, Duan noted. The ability to capture the essence of a thought, even with some inaccuracies, is a promising step toward practical applications. To illustrate, if a participant silently reads the sentence "the cat sits on the mat," the system might generate "the feline rests on the rug." While not identical, the output retains the core meaning, demonstrating the technology's potential to convey thoughts effectively. Comparison with other technologies. As reported by Euronews, earlier brain-to-text systems typically required invasive methods, such as surgically implanted electrodes or functional MRI scans, which are costly, time-consuming, and impractical for widespread use. For instance, a 2023 study enabled stroke patients to regain communication abilities using a brain-computer interface paired with an AI-generated voice. Similarly, in 2024, Neuralink, a company founded by Elon Musk, successfully implanted its first brain chip in a human, allowing basic control of external devices through thought. However, these approaches often rely on additional technologies, such as eye tracking or precise motor signal detection, to achieve accurate results. In contrast, the UTS system's non-invasive nature and ability to function without supplementary aids make it a more accessible option. While implanted electrodes can capture clearer signals directly from the brain, the EEG cap used in the UTS study produces noisier data due to interference from the scalp and skull. Despite this, the team's advancements in AI processing have enabled the system to outperform previous EEG-based technologies, achieving unprecedented results in decoding noisy signals. Real-world applications and future goals. The UTS device holds immense promise for individuals with communication impairments, offering a lifeline for those unable to speak due to neurological conditions or injuries. Beyond medical applications, the technology could also enhance human-computer interaction, enabling thought-based control of devices in fields like gaming, virtual reality, or assistive robotics. For example, a person with limited mobility could use the device to compose emails, control smart home systems, or interact with virtual assistants, simply by thinking. The research team is focused on improving the system's accuracy to reach a 90% success rate, a benchmark that would align it with the performance of advanced speech-to-text or language translation tools. Achieving this goal will require further refinements in AI algorithms, larger and more diverse EEG datasets, and enhanced signal processing techniques to reduce noise in EEG readings. Additionally, the integration of large language models, such as those powering modern AI chatbots, could further improve the system's ability to generate natural, contextually accurate text. By combining neural decoding with advanced natural language processing, the UTS team aims to create a system that not only translates thoughts but also captures the nuances of human expression. A vision for the future. The UTS research represents a bold step toward a future where direct brain-to-technology interfaces are commonplace, offering new possibilities for communication, accessibility, and human augmentation. By eliminating the need for invasive procedures and leveraging the power of AI, the team is paving the way for a more inclusive world, where individuals with severe communication barriers can connect with others effortlessly. As the technology evolves, it could also contribute to broader scientific discoveries in neuroscience, shedding light on how the brain encodes language and thought. For now, the UTS device stands as a testament to the potential of AI-driven innovation to transform lives, offering hope and opportunity to those who need it most.